Hey everyone, I'm Joanna, and I work on this project with Jessica and Eben. Together, we explore how to build a generalizable deepfake detector. The explosion of AI-generated content has made it increasingly difficult to tell real from fake images. While many deepfake detectors exist, most struggle to generalize beyond the generator they were trained on. Our project tackled this by building a model trained on a diverse dataset. Our goal is to create a robust deepfake detector that can distinguish real from synthetic images, even from generators it's never seen before. Looking at the distribution of real and fake images from our data, LSUN dominates the real sources and StelGAN2 dominates fake, highlighting strong imbalance. Category-wise, it includes non-semantic or missing labels. This heat map shows that some generators like StelGAN2 overproduce specific categories like dog or landscape, revealing strong generator bias. Given our goal is to evaluate generalizability, we selected MAT as unseen generator for our test set source because it contributes moderate 60K fake images. First step of pre-processing involved transforming target labels to 0 for real, 1 for fake. To evaluate our model fairly while controlling for source and class imbalance, we create a three-way split. Our test includes unseen celeb HQ real images and unseen fake images from MAT. For the train validation, we exclude those two and subsample from remaining sources to avoid domination. After merging and shuffling, we perform a stratified train validation split to ensure fair, unbiased evaluation. Our final split include a balanced train set from non-celeb HQ and non-MAT sources, a balanced validation of 1.2K each of real and fake, and a test with 1K celeb HQ real, 1K MAT fake. Looking closer at image source, our training and validation include diverse sources to support broad learning, while the test set uses only novel sources to assess generalization. This TSNE plot of 1K random sample shows significant overlap between real and fake image embeddings, highlighting the challenge of our task.
To validate our training pipeline, we first built a simple ResNet 18 model trained from scratch on a tiny dataset of 50 real and 50 fake images. This helped confirm that our data loading, preprocessing, and optimization were all working. The model overfits easily, reaching 98% training accuracy but only 56% validation accuracy. Next, we scaled up to ResNet 50, a deeper architecture with bottlenecks residual blocks. We initialize it with pre-trained ImageNet weights and apply stronger regularization. On the full training set, it achieved a 78% validation accuracy. To improve generalization, we adopt COMPSCI, a modern convolutional network inspired by transformer design. It retained the efficiency of CNNs but incorporate innovation like depth-wise convolutions and inverted bottlenecks. We also customized the classifier head by adding dropouts and layer norm before the final linear layer. This model outperformed the baseline across the board. It achieved 83% validation accuracy and 64% on the test set. Compared to ResNet 50, it improved real image accuracy from 33% to nearly 42%. While class imbalance remained, Connects clearly offer better generalization and robustness.
Here we show the results from our DANN ResNet 50 model, which incorporates domain adversarial training to encourage domain invariant feature learning. The architecture uses a ResNet 50 backbone with ImageNet pre-trained weights. On top of the shared features, we have two heads, a binary classifier for real versus fake prediction, and a multi-class domain classifier that tries to identify the source domain of each image, whether it's a real dataset like FFHQ or a fake generator like StyleGain2. Crucially, we use a gradient reversal layer between the feature extractor and the domain classifier. This allows the model to learn features that are discriminated for classification but invariant to the domain, which should help with generalizing to unseen distributions. We use standard training strategies like alpha scheduling, data augmentation, and learning rate scheduling. As for performance, the model reached 93% training accuracy and 78% validation accuracy, showing that it learned the training distribution well. However, on the unseen test domains, performance dropped to 51%, with a large gap between fake accuracy at 87% and real accuracy at only 16%. This suggests that while DANN was able to suppress domain-specific information, it may have also weakened features important for real image classification. In conclusion, while ConvNext Tiny achieved the best overall performance, our experiments revealed that DAN and ResNet50 struggle to generalize to on-scene domains, particularly for real images. Despite its theoretical appeal, the adversarial training made it harder to preserve class discriminative features. These results suggest that in our setting, stronger architectures and better inductive biases like those in ConvNext outperform domain adversarial methods. This highlights the need for better domain generalization techniques moving forward. While our models show strong performance on the validation set, all of them struggle to generalize to on-scene real domains. The DANN model in particular was sensitive to loss balancing and underperformed despite learning domain invariant features. Moving forward, we plan to explore alternative domain generalization methods like mixed style and SWOT, and to improve training diversity using richer real-world data.